Physics Lab 1, Constant Velocity. Newton's second law. The changes of momentum of a system is equal to the net force acting on the system times the duration of the interaction. The time interval delta t must be small enough that the net force is nearly constant during this time interval. In this case, the net force on the object being observed during the time it was observed is zero, resulting in a constant velocity for the object. Hello, I am Leanne. In this lab, I have observed the motion of a train that is moving at the same speed without changing the direction on a track. I compared the train motion to a model of an object with the same forces acting on it. The system I observed includes a module train car on a track. The forces acting on the car in the video include gravity and the force exerting upwards on the train car by the track, which cancels out the force of gravity downwards for a net force of zero. An initial force was provided by the car traveling down a ramp that was 10.5 centimeters high. The ramp is not shown in the video. The weight of our train car is 0.2 kilograms. The length of our car is 14.5 centimeters. The height of our car is 4.5 centimeters. The width of the car is 3.5 centimeters. The length of the track, is 1 meter. The slide shows the data used to create the graph shown on the next slide. Since the train car is moving in one direction, the result would be the same if other choices were made for the axis directions. The only effect might be to change the sign of the velocity vector. This picture is the graph difference between the model and our experimental data. I captured a video of the motion, then analyzed the video using Tracker to extract the object's position and corresponding time. I constructed a computational model that described the observations based on the physics principles of Newton's second law. I compared my model to my observations by plotting both the observed position versus time and the predicted position versus time on the same graph. The motion of the train overlays the path of the model, showing accurate predicted movement. I considered friction with the track and air friction too small to be noticed. The plus x-axis is the direction the train car is moving. The plus y-axis is the up. The plus z-axis is pointing towards the camera. No motion occurred in the y or z-axis. Only motion on the x-axis is shown. My observations appear to be in agreement with the model. Minor discrepancies can be accounted for by allowing for bumps in the track and the effects of friction on the system. This and the following slides show the Python program used to generate the model. I edited the amount of mass the object has to 0.2 kilograms. I also changed what the program thought was the position of the object to 0, 0, 0. I edited what the program thought the velocity was to 09288389513108614322097378277154. 0, 0. I obtained this by dividing the distance traveled in meters by the number of seconds of travel time. I changed the delta t to 0.033. The reason why I did this is to make sure that the model matches the frame rate we use for our train video. I also changed the total time in seconds to 1.056. I also changed the fnet to 0, 0, 0. Nothing was changed in these lines of the model program. In conclusion, the model almost matched our experiment perfectly, with minor errors that can be accounted for by the friction and bumps in the track. The end.